Hey everyone, it's me, Miss B, and um, in this video, we are looking at the Unit 4, Lesson 3, Cumulative Practice Problems for Illustrative Math Geometry. So this lesson was about half of an equilateral triangle, which would make a 30, 60, 90 triangle. So that's what this is going to cover a lot of. So looking at our first question, we want to select all statements that are true about equilateral triangle ABC. So they're telling me it is equilateral. So I want to know all statements that have to be true. Now they're giving me that the side length here is 6. So you'll notice they put a 6. And then they're telling me that this height of the altitude is x. So based on that, the first thing they're saying is that angles B and C are 60 degrees. So that would be these corners. And that is true. The entire angle of A, not just the halves of it, would also be 60 degrees. And that's true of an equilateral triangle. It is also equiangular. It has all the angles the same. So that one is true. So these would both be 60. And then the angles at the top here would actually be 30. So B says that x, so x right here, is 3 times the square root of 3. C says that x is 6 times the square root of 3. So since I saw that these are giving me two different values of x, I figured we'll tackle both of those at one time. The ratio on a right triangle, like this one, if I just look at half of it, is that our short leg is going to be half of the long leg. So actually, they're already using x. I'm going to use a different variable here. So let's use, I'm just going to use y because sometimes when I write the letter s for side length, it kind of looks like a 5, and I don't want to confuse you or me. So if this is 2y, this would be y, and that would make our long leg y times the square root of 3. Or the ratio you can think of without the variable included on it is just going to be 1, 2, and the square root of 3 for the ratio, right? So 1, 2, and square root of 3 is the ratio. So you can also always draw a small right triangle and use that as something that you know would be similar, where it actually has those lengths. And you can use triangle similarity to help you solve these as well. So basically, we want to find the long leg in this case, which is our altitude of this equilateral triangle. How you do that? Well, easiest way is to start with the hypotenuse, divide by 2 so that you get the short leg here, and then you can multiply that by the square root of 3. So that's the process I'm going to use. So I'll draw that to get down here, we're dividing by 2, and that would give me that this side is 3. And then to get up here, that would mean that this is going to be 3 times the square root of 3. So that was one of the answers that they gave me, 3 times the square root of 3. So that is the answer I'm going to pick. So B works. And that means I know that C does not work because it is not 6 times the square root of 3. It can only be one of those at a time. Then we have D and E. So D says that triangle ABD, so ABD, that is this one here on the right, that is congruent to ACD, which is this one here on the left, and that's going to be true. I don't necessarily have to write out the reason why, but we can see that they would both have right angles. They're both going to have 60-degree angles that we're told are congruent. They're both going to have right angles, and they're going to share a side here. So that's a leg, and this would be a hypotenuse. So these would both have hypotenuse leg for their congruence, just so that you're confident with me telling you that, and there's a mathematical theorem behind it. The other thing here is that BD and CD are both 3 units long. Well, I found that CD should be 3 units. If the triangles are truly congruent to each other, BD would correspond with CD, so they should, yes, indeed, both be 3 units long. So the only one that was not true here is C, that x is 6 square root 3, cannot be true. For question 2, now I'm going to actually apply a variable here, x, because they didn't define one, and I like to use x as my variable for my ratio here. It helps me solve, and then if I have a number, I actually write that that is equal to the variable expression that I would normally put on that side. So now I know which piece belongs where. Once we have the hypotenuse, it's possible, but it's more difficult to just jump straight from the hypotenuse to the long leg. It's easiest to go the path of finding just x first, or solving for x, and then plugging it in to find your x root 3. So if I was to find the length of each leg, I can do that by dividing both sides here by 2, and then I can get that x equals 5. So I know I can say this is 5, and in order, once I plug that in, this just becomes 5 times the square root of 3. So I can say, I'm just going to write them out so that I actually have like a definitive answer here. I'm going to say AB is equal to 5, and that BC is equal to 5 square root 3. And these are my formal answers to that question. Now the next question here, they say an equilateral triangle has a side length, and what is the area? Now again, they're asking us area, and it's not something we covered in class, so let's actually talk about the area formula, and I'm sorry that I forgot to mention this to my class, but let's draw an equilateral triangle first and then look at the area stuff, because our formula is going to be a bit different. Yesterday's assignment, we had the area of a square, and that was s squared. So here we will look, I'm just going to try to freehand an equilateral triangle. That's going to be probably as close as I can get it. And I'm just going to shrink it so it's not covering my whole thing here. Okay, so shrink it, and then I'm going to zoom in so you can still see it better, but I just don't want to cover the words. Okay, if we draw an well, I'm not going to draw an altitude first. Let's actually label what they gave me. It has a side length of 10 units. That means each side is 10. I know all of the angles are congruent. They're all going to be 60 degrees. So I can do that. The area of this, the area of any triangle, is going to be 1/2 of the base times the height. Now, we actually need a right angle between our base and our height. So we are actually going to draw that altitude from the top corner to the middle of the opposite side. That's going to be our height. The other way you might see this is, so I'm going to put a little or in between here. You may have seen this as base times height over 2. That is the same thing. Those are equivalent equations. So if whichever one you're more comfortable with, you can use that one. I'm used to using 1/2 base times height, so I'm going to use the first one. So applying that, let's actually draw in the altitude, or in this case, what will be our height. So I'm going to label that H. And then 10 is our base. It is the entire flat bottom side of your triangle, whichever side you are tipping it onto. And in this case, it's going to be 10. So in order to find our area, we need to find what would now be the long leg of a 30, 60, 90 triangle. If 10 is the hypotenuse, that means this was our 2x. So our single variable for x, if we divide by 2, would be 5. And then this we would multiply because this would be our x root 3. So we're going to multiply 5 by the square root of 3. This is going to be 5 square root 3 for h. So now plugging those pieces in, we would have that the area of this triangle should be 1/2. The base is 10, and the height is 5 square root 3. And we're just going to simplify here. Now, you have the option, just like on the equation on the right, you can multiply things out first and then divide by 2. I'm just going to multiply this 1/2 with the 10 because I can see that I can take half of 10 or divide 10 by 2, and I'll just go from there. But you always have multiple options to work your way through most of this. So your area is going to be now 5, because I'm saying that these would make that, and multiplied by 5 square root of 3. When you multiply this together, you'll get that the area is 25 square root 3. And that's our answer. It's a very tall box. There we go. Now, this doesn't necessarily have a kind of trick built into it the way the square one does, but still fairly straightforward. You would just probably need the area of the square formula. Question 4 is actually from yesterday's lesson, so Unit 4, Lesson 2, or the lesson that comes right before this. And it says, find the lengths of the legs. So I'm going to apply the same idea to this. I'm going to use x as the variable. Like I said, s just kind of, it looks like a 5. I actually read it as a 5 off of the paper, and I'd rather not make things confusing. You're welcome to use s or x, but I will show it with x. So if this side is x, that means this side is also x, because this is a nice isosceles right triangle. And then the hypotenuse side is x times the square root of 2. So we're going to use the hypotenuse side equation in order to solve for the other sides. Now, this also means that there's a pattern to this. And so you'll notice the pattern, if possible, will always end up being whatever this number is divided by 2 and multiplied by the square root of 2, because that's the process that we take. So half of this would be 5, and then times square root of 2. So you'll see that our answer will actually come out to be 5 root 2. Let's actually find it here. So dividing by square root of 2, we end up with x equals 10. But in order to make things not irrational, we have to multiply by square root of 2 on the top and on the bottom in order to actually make the radical go away in the denominator. So this would be x equals 10 times the square root of 2. And then at the bottom, we get the whole number 2, which is going to simplify into 5 times the square root of 2. So each side, I'll just write it as a sentence. I guess the legs are each 5 square root 2. Normally I would look for whatever letter name they gave to these, but this triangle doesn't have letters defining it as like A, B, C, or anything like that. But yeah, so the legs are each 5 root 2, and that is going to be a pattern that you'll notice. It should always be half because we're always going to be dividing by the square root of 2, and so these will always be in your denominator when you're trying to go from the hypotenuse back to the leg. And you'll always create a 2 there, and that will divide with whatever your hypotenuse value was. So you can use that to your advantage if you recognize that pattern. Otherwise, you can just write out your variables and solve your equations like this way. So that's the front of the page. Let's flip to the back and do the rest of these here. So this is more review from the previous unit. A square has a side length of 3 units. What is the length of the diagonal? And show your work. So I am actually going to show the work here. If it has a side length of 3. Now this one, they're leaving their answer, I believe, in a format I would not suggest. But to each their own. This is not quite a square. It's a little bit more of a rectangle. That's going to bother me. This is probably still a rectangle, but at least I can manipulate it a little bit. Okay. The side length is 3 all around, meaning this creates 45, 45, 90 triangles when we cut it in half. And the ratio there is that if the side is x, then the hypotenuse is going to be x times the square root of 2. So that means hypotenuse is 3 times the square root of 2. So, oh, I was thinking if they gave this to us the other way. I know I said they might have left it in a format I don't agree with. I was thinking they were trying to say that the hypotenuse was 3 and have us solve for the side when I first glanced at it to make that. Our actual answer is this one right here, and it is in a perfectly fine format, so that was my bad. That then brings us to question 6. We have a step with a height of 5 inches and a ramp that starts 4 feet away from the base of the step. And it makes a 5.9 degree angle with the ground. What can you say about the angle that the ramp would make with the ground if the ramp starts farther away from the step? So let's just draw a representation of what they mean. So we'll say this is 4 feet, or because they do the step in inches, this is also 48 inches. And then the height of this is 4 inches. I'm sorry, 5 inches. And then we would have an angle here with the right angle. Now they want to know if I take the end point of that triangle and make it further away, what happens to the angle? Let me see if I can actually make this dynamic with my triangle drawing tool. Yeah, okay, so you can see as I stretch it further away, the point that I'm actually moving on the far end, as I move it closer, you can kind of see the angle become bigger and bigger and bigger to the point where it's almost 90 degrees. The closer I get it to it, it would actually snap to be 90 degrees as a straight line. So as I move this further away, everything else is staying the same, the height of the step, and actually the height of the step is the only thing staying the same, and the right angle. The angle that I'm dragging away from it is actually going to decrease the further away it gets. So I like having that image in there, but we don't need it, so I'm going to erase. But hopefully seeing that in motion made more sense for it. So we're going to say that the angle would decrease if the ramp starts farther away. It would become less steep. Question 7, we have segment A prime B prime is parallel to segment AB, and then we want to show all of our work. They're going to ask us to find the length of segment A prime B prime and then B prime B. So you may be used to seeing these flipped around a little bit. I'm used to seeing the parallel sides be like this, and so I would normally see this triangle this way. But same ideas apply. We might call this like the side splitter theorem stuff, where we can compare these two to find B prime B. But because A prime B prime is the entire length of the side here, we have to use whole side lengths of our triangles in order to actually find that, because we have to compare things that are corresponding. So the length of A prime, B prime. Okay, so I am going to compare the small triangle and the big one, so the 3 and not 6, but the whole thing here, which is 9. I'm going to say that to find this, we would say 3 is to 9 as A prime B prime is to 12. Now, the fraction on the left, I can actually reduce before I cross multiply, but just doing the cross multiply straight away works as well. So I'm going to say that I'm just going to do the cross multiplication here, and 9 times whatever A prime B prime is will be equal to 3 times 12, which is 36. So I can then divide both sides by, not by 4, my brain's jumping a step ahead. Dividing by 9 here and on the other side would leave me with 4, so A prime B prime should be equal to 4. So that's for my first answer. And this one goes here, so I can, I don't know, just put an arrow. I'll do my other work in blue so it stands out a little bit more. They want to know the segment length of B prime B. That is this segment right here. We can use the side splitter theorem for this, and we do not have to use 9 for the entire side. We can just use 2 and B prime B, and 3 and 6. So I'm going to use these ones down here first. I'm still going to compare 3 and 6. So I can say 3 is to 6 as 2 would be to the length of B prime B. We're going to cross multiply, and we can say 3 B prime B is the same as 12. And if you divide both sides by 3, you'll get that B prime B should also be 4 units. And that's that question. And since that's our last one, that makes the end of the whole homework assignment. So this has been the homework assignment, or the cumulative practice problems, for Unit 4, Lesson 3 of Illustrative Math Geometry.